Hello, my name is Karl Schmeckpeper, and I will be discussing our work, Reinforcement Learning with Videos, combining offline observation with interaction. RL is difficult, requiring large numbers of samples to accomplish even simple tasks. Collecting example trajectories through teleoperation can speed up learning, but gathering these trajectories is expensive and time-consuming. An alternative approach would be to use observations of humans, as people can easily accomplish many tasks. Therefore, we ask the question of how we can leverage observations of competent human behavior in order to improve the performance of robots. Our general approach is to put both the human observation data and the robotic interaction data into a shared replay pool and then run a batch reinforcement learning algorithm on it. This approach is appealing because of its simplicity, allowing us to leverage existing RL and exploit future advances in the field. However, it presents three challenges because offline video has no actions, has no rewards, and can exhibit substantial domain shift in comparison to the robotic data. We show that simple approaches can solve all three of these challenges. We take close to the simplest possible approach to reward prediction. We assume that the trajectories in the observation data are successful and that the rewards are sparse. The reward of any state-next state pair is then a constant small value if the state is not terminal and a constant large value if the state is terminal. These constants can usually be read off the environment. Despite the naivety of this approach, it performs remarkably well in a variety of environments and with different qualities of observation data. We train an inverse model on the interaction data and use it to predict actions for the observation data. This simple approach to learning from action-free observation data has also been successful in prior works, including our prior work on learning predictive models from observation and interaction. In order to overcome the domain shift, our inverse model and the reinforcement learning algorithm operate on a domain invariant encoding H, rather than on the raw observations. We learn this domain invariant embedding using adversarial domain adaptation. We additionally find that incorporating a small amount of paired data significantly improves the quality of the learned embeddings. First, we examine the effects of different qualities of observations in the simple acrobat environment, where an agent must swing up a double pendulum. We train an RL agent on the acrobat task and gather observations from it at different points in training, giving us sets of observations with different success rates and achieved rewards. We show the achieved reward versus the number of environment steps for the three different qualities of observations. In all charts, the dashed line shows the true rewards of the observed trajectories. Existing methods of learning from observation, BCO and ILPO, shown in blue and red, perform poorly when given low reward observations, while our approach, orange, is able to reach much higher rewards while learning from many fewer samples than standard RL, which is shown in green. Next, we evaluate our performance on simulated robotic tasks, namely pushing and door opening. These tasks are challenging, as the robot only receives a sparse binary reward, and in the case of the visual door opening and visual pusher tasks, only receives raw pixel observations. Our approach, in orange, is able to significantly reduce the number of samples required to learn these tasks in comparison to the standard reinforcement learning approach in green. Finally, we consider two tasks using human data, pushing an object and opening a drawer. Unlike the fully simulated experiments, both of these tasks exhibit substantial domain shift, visually, in the morphology of the agent, and in the dynamics of the environment. We used 300 frames of paired data in the pushing domain and 500 frames in the drawer opening domain to aid domain adaptation. The robot data in all pairs are taken from random robot exploration and automatically matched to humans' observations. Our approach is robust to imperfect pairing, such as the numerous times where the human hand is in contact with the puck while the robot is not. RLV, orange, demonstrates improved performance over standard RL, green, requiring half as many samples to achieve the same level of performance, due to our ability to exploit the human data. We also show better improvement than RL augmented with R&D, an exploration bonus in blue, showing that our approach does more than simply encourage exploration. For more information, please visit our website.